lessons before spring break, standard form is used mostly when we are looking at for the y-intercept. This is the place where that function touches on the y-axis. The good news about the factored form is that that helps us to identify the zeros or the x-intercepts of a function. Remember that each little grouping, when we set it equal to 0, will help us to identify what are those x-intercepts. So in the set 2 problems, 5 minus something is 0. So we know the something has to be 5. Something minus 1 is 0. So we know the something is 1. So we have a y-intercept of -5 for this function. We've got our 2 zeros. And then I'm not sure if you remember this, but I'd like to go over a little bit about where to find the vertex. So if I know that I have a y-intercept at -5, I'm going to go ahead and put that on here. I just drew a makeshift x and y axis on my paper. And I know I have an x-intercept at 1, 2, 3, 4, and an x-intercept at 5. One of the questions you guys were having a hard time with at the end of the week before spring break was identifying the x and y value of the vertex. I think it was in lesson 11, we figured out by experimenting that when I know the zeros, I know that the vertex is halfway between. So something that we need to do is find out, okay, well, if I know the x value is 3, what is the y value? So we plug it back in. You can plug it into the standard form, or you can plug it in to the factored form. So I'm going to plug it into the factored form because it looks easier. 5 minus 3 times 3 minus 1. So I have 2 times 2, which is 4. 1, 2, 3, 4. So my vertex, this is kind of messy, sorry. My vertex is up here. And that makes sense for set 2 because notice that the a value, or the number in front of the x squared, is negative. So I know it's going to make a dump. Instead of a minimum, I'm going to have a maximum. So that works out nice because it goes through that y-intercept that we already put on there. Please just pretend like this is nice and rounded up here. All right, let's move on to the next part. And then we're going to be, oh, I'm sorry, before we move on. Check this out. Look at that vertex form. Do you see that number 3, 4 in there? Well, here's the 4. And the 3, interestingly, be thinking about that as we move on. Okay. Problem number 2. Here are 2 sets of equations for quadratic functions that you saw earlier. In each set, the expressions that define the output, or the y's, are equivalent. Set 1, just like on the first page. Set 2, which I really wish they'd move that Q over. The expression that defines h is written in what we call vertex form. We can show that this is equivalent or equal to the expression written as f by expanding the expression. So if I focus specifically on this left side, a lot of times when we see things like this, a lot of you will square the x and you will square the 2 and you will actually miss out on a term. Because if I square x plus 2, that is the same thing as me saying x plus 2 times x plus 2. And if you remember whenever we did the distribution with the boxes, with the diagram, we have x squared. 2 times x is 2x, 2 times x is 2x, and 2 times 2 is 4. Combining like terms, you'll notice we missed out on a term. We have x squared and we have 4, but we missed out on 4x. So be careful when you square things that are all in parentheses like this, and don't just square the individual terms. Remember that this means 2 of those being multiplied. So over here we've got what we just did with the boxes here. Here is that. And then we have this minus 4 at the end. So it takes away, the 4's go away because we've got 4 and negative 4. We're combining these terms. So notice that this vertex form is equivalent to g of x, the factored form. And we know if we distribute these, it is equivalent to our standard form up above. So the main thing we're trying to get out of this lesson today is becoming more familiar with a different form and identifying what is the benefits of this form. So number 1 says, show that the expressions of R and P are equivalent. So we're going to do the same thing they did, but we're going to work on R, and we're going to make sure that when I multiply it all out, I get the same thing as the P function. Before we do multiply -1, we're going to go ahead and write x minus 3 times x minus 3 because I don't want us to lose a term. We have to put a +4 on the end for later. Okay, so we can either start distributing the -1 or we can take care of this first. I think most of my students will want to take care of that first because we've done so much with diagram. X minus 3, x minus 3. So we have x squared, a -3x, a -3x, and a 9. All right, so I'm going to change colors because this is getting very messy. We're going to have -1 times x squared. We're going to combine those like terms, -6x plus 9, and we can't forget the +4 has to come down. All right, so let's switch all these signs, or multiply all this by -1. All right, and then when we combine these two little integers over here, we have -x squared plus 6x minus 5. If you notice, that is our P. So we effectively showed that the R and the P are equivalent. So when you come to these kind of word problems in the lessons, you have to try to figure out what are they looking for, and you have to prove it using math. And we just did that. Here are graphs representing quadratic functions. Why do you think these expressions, such as those defining H and R, are said to be in vertex form? Pay attention to the shape of H and the shape of R. And where this is coming from, in case you don't see it, H is up here. That's the function H. And R is right here. So see if you can notice something about them. A hint would be that these are in vertex form. So pay attention to what is the vertex on that point. This is -2, -4, and this vertex is 3, 4. Now look back at the equations, if you can see through all my junk. There we go. So I'm noticing that the y-intercept is at the end. But I'm noticing that the x, not the y-intercept, the y-value, the x value is the opposite of what is inside the parentheses. Instead of it being a +2, the actual x value of the vertex is negative. Instead of it being a -3, the actual x value of the vertex is positive. All right, keep on trucking. Oh, wait, before we go on, let's just recap a little bit about what we did last week before spring break. Notice on this problem, my x-intercepts, or my zeros, are 0 and then not 4, but -4, because this little piece, we have to set that equal to 0 to find out where it touches. Here we have 1 and 5 on the right graph. If you put a 1 in there, that gives you a 0, and if you put a 5 right there, that gives you a 0. That's why they're called the zeros of the function. And then also notice, you can't see the y-intercept over here because it's way down here, but you can see the y-intercept of the first graph. Okay. Problem 3, playing with parameters. Using graphing tech, graph x squared, then add different numbers to x before it is squared. For example, like don't add the number after like last week. We're going to put it inside the parentheses before the squared. and then come back in and record what you noticed. If I were you, I would pause this video and go to Desmos and try this. Don't forget that when you're in Desmos, in order to get a squared, you have to push Shift 6. Okay? So for me, mine looks a little different because I'm on an iPad. But I would do, okay, x plus 3. Mine has a squared, but yours does not. You may want to put an x squared function in here just by itself. So you can remember, okay, the blue is my OG, my original graph. And then what happened when I added 3? Did it go to the right or did it go to the left? Okay, then we're going to go in here.
Is anyone interested in going to Coach Kinser's store? You may go at this time.
If I subtract something, remember that the blue is my original. If I subtract 3, notice what happened. This graph moved to the right. So I'm going to go back to the notes. And I'm going to record that a positive change in the parentheses moved my graph to the left. And a negative change, a minus sign in there, minus, let's say minus 4, doesn't really matter, moved my graph to the right. Which is kind of funny because that's the opposite of what we were doing with the y-intercepts. Because remember, if I had like x squared plus 3, it moved up. And if I had like x squared minus 4, it moved down. So the x's are backwards from what the y's are doing. Okay, the next part, graph this thing, experiment with each of the changes by adding constant terms. For example, we'll take this little guy and then we're going to do plus something, and then we'll take a same function and we're going to do minus something. So you can pause it if you'd like, or you can just watch me do this with the Desmos. So we have that, which this guy already moved to the right 3, but now let's try adding 5. Ooh, so now, just like with the standard form, when we have that number on the end, it did move up. Now let's try, if I do subtracting 7. Well, looky there, it moved to the right. This is my vertex. It moved to the right 3 and then down 7. Notice this is the vertex, 3, negative 7. If I change this to adding 2 and going down 7, notice this is now negative 2, negative 7, because that's our vertex. It's the opposite of the x's, and then the number on the end is the true up and down value. Okay, I'm going to go back to the notes. So this number actually made the whole graph go up 5. This number actually made the whole graph go down 9. So the y's are changing the up and down by that amount. Now let's try multiplying these things by different coefficients, like 3 or negative 2. Let's go do that. All right, let's try. I don't want to do too many changes at once and overwhelm you. Let's try multiplying this thing, which notice our original is the blue, and then because of the plus 2, this thing moved to the left. There's our vertex, left 2. It did not go up or down any. But let's try multiplying this thing by the number 3. Ooh, that's interesting because when we did this same little experiment in lesson 12, multiplying by a number did make it skinnier because it goes up faster. Now what happens if I multiply by 5? Ooh, even skinnier. What about 10? Ooh, even skinnier or more narrow. Now let's try doing a negative. So if I do, ooh, ooh. Okay, so the negative did something specific, and then the positive, the number 3 made it more narrow. What did the negative do though? Okay, so if I put a negative out there, ooh, flipped it over, didn't it? So that negative, just like in standard form, we have the same thing going on. That negative sign still flips my parabola over. Flips function, which the graph of our quadratic functions are called parabola. Flips it over. Now, what did the number do? Like the number 2 or the number 3. Instead of being a little graph that looks like that, it is now a more narrow, oop, that should be in the origin, a more narrow graph. So let's write that. Our numbers like 3 or 10 made a more narrow graph. The reason being that now it's going up faster because we're multiplying everything by that number. And remember in lesson 12 when we multiplied by like a half, it went up slower because it was taking that graph and multiplying, and it was going up at a slower amount. Okay. Without graphing, predict the coordinates of the vertex of these quadratic functions and predict whether the graph opens up or down. Ignore the last row until the next question. Okay, well, if I were you, since we know that negatives flip these things over, I would go through here and find negatives that are out front. Okay, there's one, and everything else is positive, so I would say, does this graph open up or down? This one's positive, so it opens up. This one's positive, so it opens up. This one's negative, so it opens down. Positive, positive, negative. This one's actually positive too, because A, well, I don't know. It says to ignore that question, so let's do that. All right. Remember that it is not the negative that's with the C or the last number, ax squared plus bx plus c. This number has to do with the y-intercept. We are talking about things that are in front of the x's. That negative is the thing that flips it over, just to recover something from before spring break. Okay, so the coordinates of the vertex. We can't see this very well because it's not there. So there's a 0. So the vertex of the first one, I don't know if you remember, but we've been seeing a difference there, an opposite value of the x, and then we have the 0 for the y. Vertex form is so nice for finding the vertex. All right, the next one. The opposite of -4 is 4, and then we have our y value stays true. Inside parentheses, opposite of -4 is +4, and then we have our 8. This guy doesn't have anything in parentheses, so that will be a 0. And then a -7. Next one, -3, -5. And the last one, -100, +50. Using graphing tech to check your predictions. If they are incorrect, fix them. Then complete the last row of the table. Okay, so apparently, because our A is positive, this thing is going to go like this. And apparently, they want us to say that the opposite of M is there and the positive N. We're not going to check all of these, but you feel free to go back into Desmos and check all of these. I'm just going to check one with you. I like this one. So let's do x minus 4 squared plus 8 in Desmos. All right, there's our original. Then we have x minus 4 squared plus 8. So our vertex here is 4, 8. And on our notes, we said our vertex would be 4, 8. So we did good. Also notice that graph does open, upwards, just like we thought. Now, if I were to change this, come on, little thing, go over here, to a negative, guess what's going to happen? Flipped over. Same vertex, just flipped over. So if you look at this little guy right here, notice it's the same equation as the first one or the second one right here. However, because of that negative in front, this thing is flipped over, but it has the same vertex, 4, 8. Interesting. Okay, what is the vertex of our bottom graph here? Beep. Looks like that thing is 3 and then a -2. Okay,